Hello, so this morning I'm going to be doing a video on all of the BIPs. Not all of them, just a couple ones that you probably have heard of and are important to the consensus rules of Bitcoin, and ones that are final on the standards track. So this probably will help your understanding of the nuance and the consensus bugs and everything that has to be bug for bug within the Bitcoin code base or network. So let's get started. Alright, so these BIPs fall into a few categories. I have them separated into malleability fixes, voting, and features. That doesn't cover everything, but I think it covers most things. So malleability, what is transaction malleability? This is one of the main problems that they've been solving in Bitcoin since Satoshi made it. So transaction malleability is something that happens when you have a transaction, you broadcast it, and the TXID, which is supposed to be a unique identifier, gets changed because the script sig can be changed. So this is a problem with Satoshi's design, and the reason it is expressed is actually because of another bug in Satoshi's design, which is called the leaf node weakness in his Merkle tree implementation. So that part is something that actually cannot be solved in the Bitcoin core code. It's such a severe bug that we have to live with it, and then we have to solve transaction malleability. So that is, one of the first big problems. So they're very justified in working on malleability fixes because there have been incidents in which transactions have been malleated, and the worst kind. So the worst kind of transaction to malleate is a coinbase transaction. Coinbase transactions are the ones that are the block reward. And if that happens, then you could have a chain split at a block, not just a transaction that's different. And that can be bad. So, and to be clear, when a transaction is malleated, all the outputs stay correct. It's just the identifier gets messed up, and it makes a lot of other logic messed up. So BIP 34 is the first swipe at this because there was an incident. BIP 30 is the fix to the incident, and the incident is that there are two transactions that happened that are exception transactions that happened because the Coinbase got malleated. Coinbase transaction, of course. So BIP 34, Gavin Andresen goes, all right, this is what we're going to do. We're going to take the height of the block that's going to be mined. We're going to put that inside of the Coinbase, and then that's going to be committed. So no Coinbase transaction can be malleated. That's BIP 34. It's a good idea. It was done plenty early, or I guess not plenty early, but we live with that for now. So that takes the class of transactions that are from a initial block being mined. There are also all the other transactions that could be mined into a block. These are also all screwed because of, Satoshi's Merkle tree bug. So they decided, and by they I mean the core developers who had to think about the problem, that we have to solve transaction malleability altogether, which means make script sig utterly deterministic and well-defined. So Segwit is kind of the final part of that battle. Segwit takes every single transaction in the block, puts it in a Merkle tree, commits that Merkle root to the Coinbase, mounting the entire block on that Coinbase commitment, basically. A more optimal implementation, actually, I've been reading about this, is that you could take the height, like Zcash does this with the height, for example, and a lot of other like Equihash coins, keep the height in the block header instead of committing it to the Coinbase. You can do the same thing with Segwit, actually, but no coin has yet. BIP66, this is the DARE-SIG malleability, so, it's a component of OpenSSL regarding signatures that has a lot of values that it can take, and it doesn't need to be able to take them all, and they pruned the amount of values it is allowed to accept. That's BIP66. And BIP147 is the null dummy fix, which is similar, but basically it's about P2SH having some interesting properties where if you go to the end of it, you're not able to, it basically allows anything to go off the end. This changes it to only allow some sort of well-defined null dummy. And so those are the initial malleability fixes, and BIP62 is like an overview of the problem I just discussed, but it's a little more technical. So BIP30, I put these in purple because they're, let's call it exceptions. BIP30 is the 2 blocks that have been thrown out when they had to fix things for BIP34. And BIP42, what was BIP42? BIP42, this isn't really a malleability fix, but it is consensus critical. It actually is a C++ problem with Satoshi's implementation that counting to 21 million was not sound, didn't work right. You could go over 21 million, etc. So Peter Will found that in time, fixed that. So the 21 million is indeed a hard cap. Alright, so next we'll do voting. Alright, so next we have the voting section. And voting in Bitcoin is pretty cool. BIP9 is a way of doing miner activated soft forks. So you basically, as a miner, you're mining blocks anyway, right, for the network. You are able to signal support for a given soft fork. And this is cool with your version bits. This is a system basically better than having the block version increment each time. You do it with a bit mask, and then you can do it without being sloppy. Yeah. Alright, so now we have the voting components they've added. BIP9 is really the driver for this, and it allows for miner activated soft forks to happen. And a miner activated soft fork is something that a Bitcoin block / transaction miner will signal in the block itself using version bits to say what they feel about a upcoming proposed fork. So BIP65 was one of the successfully activated ones. It is op check sequence verify, and also I think op relative lock time verify, and those are 2 different opcodes that are added that allow you to use a sequence number, which is like an iterating nonce type thing, and a lock time to build transactions. It's an opcode. And BIP141 is another one, but guess what that one is? That's your Segwit. So Segwit activation, and I suppose I should start writing these up here so we can keep track. So let's do CSV Segwit. We'll call this version bits. This one is height in Coinbase, right? Segwit. This one is DARE related stuff. And 147 is what? Null dummy at the end of P2SH. These are the bad Coinbases. and this is bad 21 million. All right, great. So yeah, check sequence verify and Segwit both were activated through BIP9. Now, Segwit has a very funny history because as they're activating Segwit, you guys remember Segwit 2x, and then similar to that, there's the discussion of Bitcoin Cash. So it was a tumultuous time, and part of that resulted in BIP 92 happening. So BIP 92, they take this rule that they had set ever since I think BIP 34. This had been in place, and it was reused for BIP 9. It's 75 is the agreement, and then 95 is the point of no return. So at BIP 92, something you can do is, after the 75% point, change it to 80% for the point of no return. And so that's what they did in BIP 92. This was during the Segwit 2x, and this was just to let miners, dig in further in their immediate consensus of the problem. It's fully legal, reasonable, maintains the chain. Very nice trick that they did, and it wasn't really needed, I think, because Segwit 2x just kind of bailed. But they've done it before, so they've even reduced this to 80% on a follow-up soft fork. And BIP 148 is not really something that was voted for, but it's an interesting similarity. It's just a BIP where it says 1 month until Segwit activates, get your nodes ready, or there might be a chain split. And in fact, there is no legacy chain, but if there were to be like a Bitcoin no Segwit, that's when that would have had to happen. All right, and finally we'll do features. All right, and the last set of BIPs are features. So these are things that have been added to the protocol over time. So they're all, you can say, opt-in, or they're user-activated soft forks, as opposed to these BIP9 miner-activated soft forks. So BIP 16 is pay-to-script hash, which lets you do a new class of transaction, including multisig. BIP 22 and 23 and 145 are all regarding get block template. So this is the miner that is in Bitcoin and that Stratum uses and things like this. Get work is the old one, and Luke Dasher worked a lot on get block template, and 145 was a follow-up for when Segwit was deployed. We've got BIP 32 as well, and there's like BIP 44 and a few others, but BIP 32 is HD wallets. So an HD wallet, really quickly, is a normal address, which is a private key and a public key, or a public key hash. BIP 32 lets you take those private keys and basically hang them as a chain. So you have a single private key, but it's really your mnemonic seed words, and below that you have an entire list of keys. This gives you a lot of good assurances, like it's easy to not reuse addresses, and you can use your other addresses as change addresses and stuff like that. So BIP 32 is HD wallets. We've got BIP 70 and BIP 75 and everything in between. Those are payment protocol changes. So like the Bitcoin URI and some stuff about the headers in HTTP and things like this. And BIP 173 finally is Bech32 addresses. So Bech32 is P2WPKH, but they call it native Segwit. So it uses a different type of encoding other than base 58 check, all lowercase, and starts with BC for Bitcoin. I'm sure you've seen them around. So those are all the BIPs I wanted to talk about today. They're fairly straightforward, but when people talk about Bitcoin being complicated or, bug hell, they're kind of right. It's just a long story. And as I discussed at the start, it kind of began with the leaf node weakness in the Merkle tree. I'll put a link in the description where Sergio Lerner talks about that and talks about how to fix it. But yeah, thank you for watching. Leave me any questions you have. I'm sure you have some. I'll put a final frame up where I fill in the names for the features section. And thanks so much. Have a great day, guys.